This lecture is on finding volumes of solids of revolution using the shell method. First thing to notice is that compared to the washer method, which I show above, where the washer method you have your representative rectangle perpendicular to your axis of rotation to get either washers in this case or disks if we have an inner radius of 0. The shell method, for the shell method, we have the axis of rotation parallel to our representative rectangle and we get cylindrical shells. And so immediately the geometry of it is slightly different, and so therefore formulas involved will be different, the way we set it up will be different. So looking first at a way we can use washers or disks to do a problem, but then where shells is better. If we're taking this region defined by y equals x squared plus 1, the lines x equals 0, x equals 2, and y equals 0, and revolving around the y-axis, what happens is we have a horizontal rectangle if we're going to use disks and washers because we want to be perpendicular to our axis of rotation, which is the y-axis. But we have one integral going from vertical line to curved line, another one from vertical line to vertical line. So we have two different integrals. The integral for the top part is given down here. We have pi outer radius squared, which is 2, on the inner radius squared, which is this x, and we solve y for x, and we get x is rad y minus 1. And in the bottom part, rather than using an integral, we just set it up as a cylinder of a radius of 2 and a height 1. Now you can go through and do all that, that's fine, but it's easier in general to try to use one integral if possible. And so exact same setup, but now what we're going to do is use a rectangle parallel. So we have our vertical rectangle, which is going to be parallel to our axis of rotation, and when you do this you get cylindrical shells. And so it'll be a different formula. So this is how we can set it up. We have this thin hollow cylinder. It's the lateral surface area of the cylinder times its thickness. In this case the thickness is this infinitesimal horizontal bit dx, and so our limits of integration would be with respect to x. Our formula for the lateral area of the cylinder is 2 pi rh. The radius is from our axis to our rectangle, so an x value of 0 to some random x value, so that's x. And our height is the height of our representative rectangle, which is y down to 0. And so y in this case is x squared plus 1 down to 0 is just, well, x squared plus 1. And so we have a single integral. And because it's with respect to x, we would be integrating from 0 to 2. So here's how we put it all together. We put this part in our integral. We go from 0 to 2. Of course, the actual integration itself is rather simple, and you can use a calculator for a lot of that. The main idea is the setup. Now for this one, we want to go around the y-axis. And this one, it's not just preferable to use the shell method, it's really just about necessary, because if you're going to use disks, you would have to, or washers, you'd have to have a horizontal rectangle. You'd be going from the curve to itself, which has some problems. You'd also have to solve it for x, which has all sorts of other problems. Very inconvenient. Much better to use a vertical rectangle. So you're always going from parabola down to x-axis. And so here it is. We have our vertical rectangle right here. 2 pi radius times height. The radius is again from an x value of 0 to an x value of x, so that's x. The height of the rectangle is y, so 2 pi rh dx, because this is an infinitesimal horizontal bit, so it's a dx. Putting that all in terms of what we have, this is our radius, this is our height. X is going from 2 to 8, because we're not going from 0 to 2 or 0 to 8, it's 2 to 8. That's where the area is we're rotating. And we put it in calculator, we get some value. So again, if the representative rectangle is parallel to the axis of rotation, use the shells. If it's perpendicular, it's washers or disks. Now I'm going to go through about 4 or 5 more examples, just setting up, a couple solving, but mainly setting them up. In this case, you have an area determined by the line y equals 1 minus x, and the two axes in this first quadrant area, and we're going to rotate it about the y-axis. You could use disks or shells. We'll go shells. So vertical axis of rotation, because we want to be parallel to our vertical rectangle, so we're parallel to our axis of rotation. It's a dx. X in this case is going from 0 to 1. Because it's shells, it's 2 pi and then radius times height. Here's our radius from 0 out to x. Our height is from the top of the rectangle to the bottom, which is the height of y. So 2 pi, 0 to 1, x. In this case, y, of course, is 1 minus x. There's our integral. You can put it in the calculator and get an exact value in terms of pi or an approximate answer, but here's the actual fundamental thermocalculus version. So we go through and we get pi over 3. Of course, this turns out to be a cone with a radius of 1 and a height of 1, and you could verify that it's pi over 3 using a cone formula as well. In this case, we have this area given by y equals 2 minus x, and x equals 4 and y equals 0. We're rotating around the x-axis using shells, so that's a dy. Y in this case is going from negative 2 up to 0. Parallel rectangle compared to the axis, so that's shells, of course, so 2 pi. The radius in this case is from your axis down to your rectangle, so that's a distance of negative y, a little bit trickier now. And the height is from an x value of 4 to an x value of x, because this one's changing as the rectangle moves through the region. So that's going to be a height of 4 minus x. We have to have everything in terms of y. We know if y is 2 minus x, then x will be 2 minus y. So plug in 2 minus y for x, and then we can simplify it before we would go ahead and actually integrate it. This is a good comparison problem. We're taking